Okay, so the idea here is to calculate the magnetic field due to these two wires at the point P. Of course, the wires make magnetic fields everywhere, but we're only interested in the magnetic field at point P due to these two wires. So the first thing we need to do is just see what does the field from the blue wire look like. So this X means that it goes into the page. And so if we use the right-hand rule, in other words, if I point my thumb away from me into the page, my fingers will naturally curl in the direction of the magnetic field. It'll look something like this. So the idea is that the magnetic field curls in a circular direction around the wire. And the reason why my arrows go clockwise is because if I use that right-hand rule and I put my thumb into the page, my fingers curl in the clockwise direction. So that is what the magnetic field from the blue wire looks like. What about the magnetic field from the red wire? Well, that also makes a circular field around that wire, only now, since that current is coming out of the page, I point my thumb out of the page, and now the arrows go in the counterclockwise direction because when I point my thumb out of the page, that is the direction my fingers curl. So the red wire makes the magnetic field shown in red. The blue wire makes the magnetic field shown in blue. We really only care what the magnetic field looks like at point P. So let's dispense with the rest of the circles. The only point of doing this was to figure out the direction at point P. So we'll get rid of the circles. Now we're left with these two vectors. So this is the magnetic field from each wire represented. The blue wire points strictly to the right. The red wire points down and to the left. You know that when we add vectors, we need to add vectors the way that you add vectors, which means you put the tail of one at the head of the other, and then ultimately what we're going to end up doing is making components. Okay, so the first thing we have to do is, how strong is each field? Okay, well, the field from any wire is mu naught I over 2 pi r. I say any wire, really, I mean from an infinitely long wire. Of course, if it's not infinitely long, you have to use Biot Savart, but in this case, these are infinitely long wires. That is how long each of those vectors is going to be. In the case of the blue wire, it's the distance a away. In the case of the red wire, it's the distance root 5a away. And so if I want to just label the size of those arrows, that's what they look like. In other words, I've labeled the magnitude of each magnetic field, and I need to do that before I can find the resultant magnetic field, which I do by looking at components. So I needed to put this angle theta here because ultimately this guy that's diagonal has to be broken into an x component and a y component so that we may add in the normal way that we add vectors by components. So the only other piece that's missing here is we got to know what is this angle theta. So notice this is just the strength of the red field. This is just the strength of the blue field. This cosine theta tells us to look at just the horizontal component. Okay, so we got to do a little bit of geometry, which is not fun, but if I get rid of all the noise so I can just see theta, then we see that this angle theta is actually the same as this angle theta. You may say, why? Well, this is pi over 2 minus theta, and then this whole angle is also pi over 2, and so you end up with something that's like pi over 2 minus pi over 2 minus theta. Anyway, you get the idea. You end up with theta again. And so that means that the sine of theta is 2a over root 5a, so it's opposite over hypotenuse, and then the cosine of theta is a, so that's adjacent over hypotenuse. Okay, and then after that, it's just a little bit of algebra, and we're done. These problems are really tricky to visualize, and that's why you should immediately write things down and draw a picture of it. You shouldn't try and visualize it at all. You should just draw it. Okay, hopefully this helps more than confuses.